Hello all, welcome to my channel. I'm back with another video. As you can see in this video, we will be discussing about a new open source project which is out there in the market. It is uh, talked about as well, and we'll see what it is and why it is important to take note of this project. So let's start. So in this video, we will be talking about Fluss. Fluss is an new cutting edge disaggregated streaming table storage engine specifically designed for real-time analytics. So this is what Fluss is. So we will cut through we will slice and dice and see what this disaggregated, what the streaming table storage engine and other things mean in this term. So uh, at a high level, what it means the disaggregated storage is that we will have the compute engines having certain copy tied to that node, but we will also have offloaded to a distributed system which can be connected from all the servers which the cluster has, and it will be able to deliver the responses based on that. So that's how the disaggregated part comes into picture. Streaming is pretty much which is something which we have been dealing in case we are working with Flink or Kafka. So Kafka was one event store which was used as a streaming ingestion platform in many of the large tech orgs. Actually, it is still being used, uh, but it was designed for a time which I will say was not that much of cloud native, plus the that much of uh, not in a sense I will say the disaggregation of the storage and compute was not that common at that time, and hence the Kafka was tightly coupled. So coupled in a sense it was both. Let's say if you have to just increase the storage, you needed the whole system to scale. If you want to decrease, then you will have to scale down. So there was no separate storage and separate compute. It was tightly coupled. So those challenges were there with Kafka, and also Kafka was being means Kafka has a concept of events, and for analytics, that is not the right format in which the events should be consumed. Because anyhow, let's say if you want to run analytics on top of the Kafka cluster, you will have to build another system which translate the JSON or proto schemas into a table format which is suitable for analytics. And that's where this Fluss comes into picture. It tries to remove the challenges that were there with Kafka in a different approach, like they have concept of columnar storage format rather than an event-based network. So what it suggests is that if we want to have a lakehouse engine built on top of the real-time databases we have, or let's say we want to run analytics on top of those changes that is happening in different places in one unified lakehouse, then Fluss is the uh, kind of a replacement for the Kafka. So that's what this Fluss cluster will do. And the people who are building this are from Alibaba Cloud and Verberica. So Verberica is the company which was created by the creators of Flink, and they have been offering managed services for Flink, and that team is involved in building this Fluss cluster as well. What it Fluss does it has it talks about unifying the streaming and batch uh, in one particular platform built on the open table formats like Pymon or Iceberg, and it also uses offload. It also offloads the historical data from Fluss cluster to the object storage system for long-term analytics. So this is something which has been being discussed a lot, and we will see how it is different and how it works out. So if you at a high level, if we say we have this Fluss cluster which has servers which are compute engines and which will be serving the requests for ingestion as well as for consumption. We have remote storage where uh, the offloading happens, and then we have tiering service, which even further moves data from, let's say, remote storage to a lakehouse format, which can be Pymon or Iceberg. And if you say, so what we can do with this is we can combine the real-time reads, real-time data plus the historical data in a union format and serve using Flink, or we can do it serve with the batch platforms like Apache Spark, or even we can combine this with ClickHouse or other tools which support the formats mentioned in the Lakehouse storage. So this is something that we will be seeing, and the updates are happening in the real time. Also, the Fluss, the name is a short form for Flink Unified Streaming Storage. So from now, if you see, we discuss the challenges of what Kafka has, but at the same time, Flink also has certain limitations that Flink, I mean, I will not say it's a limitation, but it's an from a solutioning point of view. If we are using Flink as an compute for the real time, it doesn't have its own storage. It relies on, let's say, sinks that consume the or that where the Flink writes the data to, and then engine then takes care of everything. So what this engine Fluss is trying to do is provide an unified streaming storage for Flink. And so that's why Fluss is built from ground up to be a native integration, to have a native integration with Flink. And it replaces Kafka, but it will have native integration with Flink. And Fluss also supports offloading directly into Pymon, which is again a new table format designed for streaming use cases. So it builds on top of the work done in Delta and Iceberg and make it more real time. So I will say it is more closer to how Hoodie handles streaming use cases. From the use case point of view, Hoodie is more centered towards streaming use cases. Similarly, here Pymon is more focused towards providing a unified lakehouse for streaming use cases. So some features, some points to note is Fluss is implemented in Java. It supports sub-second streaming reads and writes. Currently, so requires zookeeper for coordination, and tables are partitioned and replicated similar to how Kafka topics are uh, replicated and partitioned. Recent data is stored on local disk, and older data is compacted and stored in Lakehouse. In case here it is Apache Pymon for large-scale historical analysis. It uses arrow columnar format for its underlying log file storage. So that's the new thing that is in picture, which allows us to do analytics at a faster rate compared to what Kafka would have provided. And the Fluss protocol is implemented using protobuf, which makes it more it's slightly more performant than the other native formats or protocols that were there. So Flask, if you see Flask cluster, sorry, if the this is, let's say, if from the use case point of view, if you see we have a Flink cluster where we will have clients. The Fluss client, Fluss Flink client, means the integration will have a Fluss client and a Lakehouse API. So the Fluss client talks to the Flux cluster for reading and writing, and this Lakehouse API is what does the reading or writing to the Lakehouse engine, which is, let's say, in case is Pymon, and there is a tiering service, which is, by the way, again can use Flink itself in the Flux cluster to uh, write offload the work which is there, offload the data which is there in the cluster to the Lakehouse system, which is in Pymon. The throughput and latency number, some of them are it provides in zero copy operations, and it is batched at 1 MB of data, and it supports compression at level 3. It is asynchronous in writes for both tiering as well as offloading, and it supports columnar pruning because it is based on columnar format, so it can support columnar pruning. So for example, let's say if there is a JSON event, I mean, so if it is a JSON event, then we will have to first read the whole JSON and then we can discard certain things. But from the source side, we can't do. But in case of Fluss, if we want to discard certain columns while read certain attributes while reading from uh, the cluster itself. That time that is possible because it has Kafka, sorry, it has columnar integration. So as I had mentioned earlier, why Kafka was challenging, like it was row-based, no support for analytic workloads, lack of native updates. So Kafka is an append-only table system, so it doesn't have an update, inefficient data access pattern because as mentioned, it doesn't have any column pruning or attribute pruning. Natively, we can implement this, but something which is not there out of the box. And it also has compute and storage decoupling, which was increasing the cost. And Flusk tries to address these things and make it more suitable for real-time analytics. For example, it has columnar storage, so that means it is not row-based. Now becomes column-based. It had support for update and change logs because Fluss supports rollable updates via the LSM. So it uses log structured merge tree, LSM tree to have different run labels and then keep the hot data in memory and offload the longer data or older data into the SS table, and then that SS table gets even further persisted as an Pymon table in the lakehouse environment. So those are the things that we is being solved by Fluss by replacing Kafka with it Fluss cluster. And if we see from the just from different aspects, and if we compare Fluss versus Kafka, so Fluss is designed for streaming analytics. Kafka was designed for streaming events. Data model Fluss adopts a lakehouse native design with structured tables and explicit schema. Kafka doesn't have built-in schema and schema enforcement, so we have to rely on a schema registry and schema validation enabled brokers. So that happens is there. But that only is present only in the enterprise version of Confluent schema enforcement. There are other solutions like BuffStream, which does schema validation natively, but that is again something which is different than Kafka. And data layout. So instead of Kafka topics, the Fluss organizes data into database tables with partition and buckets. And Fluss uses Apache Arrow for its columnar log storage model for efficient analytic queries, while the Kafka used to have unstructured row-oriented logs for if sequential scans. Mutability, Fluss natively supports real-time updates, but Kafka doesn't have any update support. It's basically like while doing the compaction, you can modify the weak semantic and do the changes, but not update-wise. Tiered storage. So Fluss uses Lakehouse as a tiered storage, and data will be converted and tiered into data lakes periodically by the engine itself. In Kafka, the tiered storage support is there in the newer versions of Kafka, but that is only for remote storage, and it's only a cost optimization. So we still have to keep the raw data or hot data in the memory of the Kafka cluster. So that's the uh, challenge in there. Architecture wise, Plus is Kafka architecture. It believes in having unified streaming and batch workloads and one computation layer. No two different ones. For example, Lambda will have one real-time flow and one offline flow. Uh, that Flux tries to unify that, and then Confluent stable flow follows Lambda architecture because that's how it is designed. Like we will have Flink to process the real-time data and Spark, let's say, to process in the batch mode. Let's discuss what are the different components of a Flux cluster is. So at high level, we have two major components. One is called coordinating server or coordinators, and then we have tablet servers. And so if we have multiple coordinating servers, we need a quorum to make someone as a leader, like primary and secondary. And for that, Fluss uses Zookeeper. In future releases, this might go away and it will it might follow a raft-based consensus algorithm to remove the Zookeeper dependency. But as of now, it is Zookeeper is there. And there are different as I mentioned, there are the different type tablet servers. So tablet servers are where the log store resides, like all the data that is going to be stored in this tablet servers itself. So it will have log table tablet for particular, let's say, bucket is there. So there will be one leader, there will be multiple replicas of the table, and it will also have KV store for KV store tables. These are primary things, and then we have remote storage where it offloads the data. So KB snapshot and log tiering happens on the remote location. Uh, the tiering service, if you see, it uses an Apache Flink job without Flink state. So what it does, uh, it moves the data from Fluss cluster to Delta Lake. As of now, what happens is latest data will remain in Fluss. The older data goes to the offline system. The historical data goes into Pymon. Older data is compacted and stored in Pymon for a large historical analysis. So this is what happens. So you have Zookeeper, you have coordinated servers, you have tablet servers, and then there is a job client, which is a Flink job, which does the optional tiering to this remote format. So now let's see how a table is organized in a Fluss cluster. So table is the fundamental unit of user data storage organized into rows and columns, and tables are stored within specific databases adhering to the hierarchical like database table and then rows and columns. Table data is divided into multiple buckets. So this is the structure that table will have multiple partitions. So by the partition column that we define, so the table will have multiple partitions. Each partition will have multiple buckets based on the bucketing column we have, like the primary key. And each bucket then will have different log tablets. It depends whether if it is a KB table, then it will have a KB store as well. And if it is append only, then we will have tablets, and each log tablet will have multiple segments, and multiple each segment will have an index file and a log file. So if it is append only, so this structure is followed. But if it is, let's say, key value or primary key table, then it will have RocksDB instance as well. So there are different what you call bucketing strategy, like hash bucketing, sticky bucketing, and round robin bucketing to define the different buckets. And so each table as of now only supports one partition key, and that partition key has to be a string data type. And automated creation of partitioning strategy only supports when creating a table. So let's say if we want to have automated partitions, we have to define at the table creation itself. We can't do it afterwards. So in Flink, sorry, Fluss, there are two different types of tables. One is log table. As I was mentioning, it is the log table only supports appending data, just like Kafka topics. And log table uses log store to store data in a raw format, in arrow format in the storage model. And then we also have a primary key table where so it will have a table which supports updates. So the primary key table also uses the log store to store change logs, and KV store to maintain the materialized view of the change log. So KV store leverages RocksDB and supports real-time updates. That's where the difference comes. And the merge engine in the Fluss at the core component, which is designed to handle the consolidate the updates between the primary key tables. So this is thing that's a difference. And if we see from a standard point of view how those two are different, is that in log table we do a append and just do a fetch, that's it. In primary key tables we have put, which is nothing but to update or to insert a new records, and we do a lookup to find anything is there or not. And then this table also emits a change data stream that can be consumed by another application to see whatever changes are happening in here, and can be emitted as in a CDC that we can leverage to populate the sinks further down. Uh, so TTL, now TTL is for automatically clearing the expired data in the table. For log tables, for example, TTM time represents the data existence time. For primary key tables, the TTL time represents the bin log existence time in the primary table. If the primary key table wants to achieve automatic data cleanup, similar to the log table, the primary key table needs to set an automatic partitioning strategy and then define the TTL, and it will remove those data. Let's see a write path. So when an update request is sent to tablet server, it first looks for KV store. So this is for in case update is needed. It will look for the KV store, and it will combine the previous row and the new row as a change log, writes the change log to the log store and uses its wall for KV recovery. Then the writes will go to the new KV store, and Flink will consume the change log and update the log stores to process the stream. So this is the flow, like update, request, receive, tablet server, it goes to tablet server looks up the KV store, the KV store then retrieves the previous row, combines the previous row plus the no, new row or the new update that has come, then it will create a change log. That change log is returned to the wall and then also persisted to the new row is persisted to the KV store. At the same time, Flink consumes this change logs from the log store and then does the stream processing. So this is how an update is made to the Fluss cluster. In case of we need partial updates, the lookup of the previous row key merges the previous row and new row to update columns and write back to the merged row. So that's how the partial updates happen. Integration with Pymon. This is the data distribution in Fluss and Pymon is clear aligned. Fluss also has in partition tables and buckets, and bucketing algorithm of Fluss is consistent with the Pymon table format. So this is, for example, the delta join with Flink removes the need for a large storage requirement for a state. So this is one use case where we can, so let's say if we have two different tables in Fluss and we want to have a join and do consume do process the data in Flink, we don't have to do that with a large what you call windowing state. We can do it with Fluss without Flink maintaining this state. So that's how this is there. And the mapping, if you see the bucket to bucket tiering mapping is there, avoids shuffle overhead, and bucket to bucket mapping avoids the data inconsistency between Flink and Fluss and Pymon. So if you see the typical windowless stream join is how here this will happen. So there is a left stream of data that arrives, there is a right stream of data arrives. The query the right table with the join key and query the left table with the join key and join the result. So this is how Fluss introduces a windowless join, and that's why we can process larger state as well using Flink. Primary key table makes this possible because it has a unique key constraint. So Flusk uses the streaming read secondary index lookup to achieve this. And when data arrives from the left stream, the right table is queried using the join key. And when the data arrives from the right stream, the left table is queried using the join key. So based on the join key and primary key, it's able to store without needing to store the whole state in memory, what otherwise Flink would have done. And we were talking about the layouts, sorry, the structure, not the structure, but the uh, kappa architecture model. So see if we have the real-time data layer and historical data layer, both are residing in one particular system, both are processed at once. Those both are combined together and consumed by one Flink engine directly. So this is what the Lambda, sorry, Kappa architecture will have as a unified batch and streaming platform. So this was the introduction of Fluss. We also have certain future roadmaps. These roadmaps are mentioned. Roadmaps is as of the date of publishing this particular um, uh, story, which was in April, I think somewhere in April, I had written this blog. So there are some things, for example, Flink Fluss will support Kafka protocol. So that will make this replaceable. Like if this, as of now, Fluss doesn't support Kafka protocol. So once it is implemented, we can simply swap Kafka with Fluss. Support for Flink data stream API to and read and write from data Fluss clusters. That is again one other change that is happening. It will support for Iceberg. So as of now, what we see is if we want to consume from a lakehouse, if we see as of now, the option is for only for Pymon. So what it will do is it will offload or convert from Pymon to Iceberg to have the same view with different engines. The reason that is being done is not a lot of compute engines have full support for Pymon as of now. For example, Spark does not understand Pymon. Only few, I think, only Doris understands as of now Pymon, and I think some of the Star Rocks maybe. So some analytical engines support Pymon, not all, and hence this is needed. So that once it has the Iceberg support, then the more different compute engines can consume from the historical layer. Then directly compact arrow files of Fluss into Parquet files of data lakes. So this is again, as of now, the compaction is not one way. Like first it gets written to arrow and then it gets converted to Parquet. So that's what it is changing from in-memory arrow to directly to Parquet is what it is being planned. Upcoming, as I mentioned, Zookeeper will be replaced by KV store for metadata storage and Raft for cluster coordination. So that's where the change will come. It will also planning to support schema evaluation, which is something needed because, for example, Kafka has, if we combine it with schema registry, we can still have some sense of schema evaluation. So that same support is being added in here as well. Also, secondary index for delta join with Flink that is being planned, and it Fluss currently utilizes tiered storage architecture to significantly reduce the storage cost and operational complexity. However, the Fluss community is actively investing in zero disk architecture, which aims to completely replace the local disk with S3 storage. So as of now, we have certain hot data which still remains in the local disk. The plans are there to completely remove that requirement as well and only keep the wall, the WAL write ahead logs in the local memory and persist that into directly asynchronously into the S3 storage. So that will make it completely stateless and we can scale up and scale down the Fluss cluster without the need to have local disk also scaled up. So yes, these are the future roadmaps for Fluss. If you find this blog interesting, do share and you can comment your thoughts of how you believe Fluss is going to change the streaming landscape. Thank you.